All right, let's dive in. We're going to try something here. We're going to draw a map, but not of a place, of an idea. An idea that has completely reshaped our world, computer science.
But here's the thing, to map this incredible world, you can't start with, a supercomputer. Nope. You have to start with the most basic, fundamental truth. The fact that every single app you use, every website you visit, all that mind-blowing AI, it all just boils down to one thing, flipping tiny little switches, just zeros and ones.
Okay, so before we start drawing any lines on our map, we've got to get two key ideas straight. These two concepts are like the bedrock of this entire field.
First up, computation. What is it? Honestly, the best way to think about it is like a recipe. That's all it is. It's the process of following a very clear set of instructions to get something done. Doesn't matter if you're baking a cake or, solving some crazy math problem, it's the same idea. So if computation is the recipe, what are the ingredients? Well, that's information. And when you get right down to it, all information, all of it, is just a long, long stream of ones and zeros. We call them bits. And when you group, say, 8 of them together, you get what's called a byte. And that's enough to represent a single character, like a letter or a number you see on the screen. Okay, got it? Computation is the action, information is the stuff. Now we can start drawing our map. And what you're gonna see is that the world of computer science is really split into these two massive continents. They look different, but you'll see they're totally connected.
On one side of the map, we've got the theoretical. This is the land of pure math, of logic puzzles. It's where people ask the big questions, like what is even possible to compute in the first place? This is really the why behind all the magic. And then on the other side, you have the applied. This is where all those abstract theories get their hands dirty. It's about taking that pure logic and actually building the stuff that shapes our world, the software, the systems, all the tools we use every day. This is where theory crashes into reality.
So let's take a trip. We'll start on the theoretical side of the map, and our first stop is a big one, algorithms. Remember that recipe idea we talked about? Well, that's basically what an algorithm is. It's the step-by-step recipe for solving a problem. You could even say they're the blueprints for pretty much any program ever written. And the whole game with algorithms is efficiency. How fast can you get the job done? Check out this divide and conquer approach. Imagine you're looking for a name in a huge old school phone book. You could start at A and check every single page, right? Or you could be smart about it. You open right to the middle, see if your name comes before or after that page, and then you literally throw away half the book. You just keep cutting the problem in half and boom, you find what you need incredibly fast. But that leads to a question, right? How do we actually know if an algorithm is good or fast? Well, that's where something called complexity theory comes in. It's all about measuring efficiency, and for that, we use something called Big O notation. It sounds kind of complicated, but it's just a rating system. It tells you, hey, if I double the amount of data I'm working with, how much longer is this thing gonna take? A great rating means the time barely goes up. A bad one? Well, a bad one means you could be sitting there for the lifetime of the universe, waiting for it to finish. And you know what? This kind of theoretical thinking is absolutely crucial for something we all rely on, security. Which brings us to our next stop on the map, cryptography.
So modern encryption is pretty clever. It scrambles up our data using math problems that are super easy to do one way, but almost impossible to reverse. Think about it. It's easy to multiply two really, really big prime numbers together. But if I just give you the giant result, trying to figure out which two primes I started with, that's incredibly hard. And that's the digital lock, the very thing that protects everything, from your emails to your bank account online.
All right, let's pack our bags and travel across that dividing line on our map. Let's head over to the applied world and see how all this theory gets put into practice, starting with software engineering.
Now, this is so much more than just typing out code. It's called engineering for a reason. It's about building enormous, complex systems that have to be reliable. And to manage all that complexity, people came up with ideas like object-oriented programming. It's basically a way to create reusable blueprints for your code, which makes it way, way easier to build and update the massive apps we all depend on. And from there, we get to what is maybe the most exciting, most talked about area in applied computer science today, artificial intelligence. The real engine behind all the AI we see now is machine learning. And this represents a huge shift in thinking. See, instead of a programmer writing out every single rule by hand, we do something different.
We just feed the computer a mountain of data and let it figure out the patterns for itself. It builds its own complex web of connections to make predictions. It learns.
So, okay, we've mapped out the two main continents, the known world of computer science. But here's the cool part. The explorers, the computer scientists, they are constantly pushing the boundaries, sailing into what the old maps called terra incognita, the unknown lands. The edges of our map are always expanding.
Look out on one horizon and you'll see quantum computing. This is just mind-bending stuff. Instead of our regular bits that are either a 1 or a 0, quantum bits, or qubits, can be both at the same time. And that one weird property could unlock enough power to solve problems that today's best supercomputers wouldn't be able to crack in a billion years. It's a total game changer. Then, on another part of the horizon, you've got blockchain. Now, you might think crypto, but it's much bigger than that. At its heart, it's just a way to create a secure, shared digital record book. And because no single person controls it and it can't be changed, it promises this whole new level of trust and transparency for almost anything, from finance to supply chains, even voting. And finally, there's this incredible fusion happening with 5G and the Internet of Things, or IoT. This is what's blurring the lines between our physical and digital worlds. We're talking about billions of devices in our homes, in our cars, in our cities, all connected, all talking to each other in real time. This isn't just a fantasy. We're building the foundation for a smarter, more responsive world right now. So when you look at our finished map, you see this vast, powerful, interconnected world. But you know what the most exciting part is? It's all the blank space. It's the parts that haven't been drawn yet. This field is constantly, every single day, redefining the very meaning of possible. Which leaves us with the real question, the big question. What new worlds are we going to discover, and what new worlds are we going to create tomorrow?
So what do you think comes next? Share your thoughts in the comments. I'd love to read them. And subscribe if you want to keep exploring ideas like this.